Good afternoon and welcome to the last EOL seminar of 2014. It's our privilege today to welcome Bart Geerts from the University of Wyoming, professor. Bart received his bachelor's and master's in geography and irrigation engineering, respectively, from University of Louvain in Belgium, and then went to the University of Washington and got his PhD in atmospheric sciences under Peter Hobbs, who some of us knew. Let's see, done lots of things, but in '99 he joined the University of Wyoming and has been a professor there ever since. He's an editor of Journal of Applied Meteorology and Climate. He's recipient of 3 awards in the last 3 years, National Institute of Water Resources, NIWR, for an Impact Award, Samuel Hake's Outstanding Graduate Research and Teaching Award, and the Faculty Senate Speaking Award, according to what he wrote down. So anyway, he'll be telling us today about PECAN. Thank you.
Thank you, Steve. Well, it is a special honor for me to give this seminar. Thank you for the invitation. I will be speaking about this campaign that you've all heard about, PECAN, Plains Elevated Convection at Night. But I need to emphasize that this is the workings of many people, several of which are here in the audience. The lead PI is actually Dave Parsons at OU. And we have a good steering committee. Names are listed there, Tammy and Conrad Ziegler are quite involved, as well as several other people, including Karen Kosibos, maybe not listed there. But, it's a very large campaign. It's funded by NSF primarily, PDM, 11 proposals funded, a significant commitment of the facilities. In fact, maybe the most significant commitment of the EOL facilities in many years, with, as listed down there, all ISS units, including the 449 megahertz wind profilers, the mobile ISS and 2 fixed ISSs, with up to 400 Gauss soundings, the 3 Dow mobile radars, also SPOL, and then the University of Wyoming King Air with WCL and a compact Raman LiDAR. A large number of participating universities and other groups, labs, and 30 to 50 students in the field. Altogether, NSF's commitment is on the order of $10 million, and then there's also participation of NOAA through the NOAA P3, and NASA through its DC-8, and then also NOAA will contribute to the deployment of the SMART-R radars and assist in the forecast effort. So, first I'll talk about undular bores and solitary wave solitons, then the low-level jet, and warm season precipitation in the Great Plains as a way of setting the background. The rationale for PECAN. Basic rationale is that much of the field work to date in deep convection has been conducted during the daytime and has ended around sunset, and that's where PECAN starts. So the key elements are the deep convection and interacting with a stable nocturnal boundary layer. Low-level jet is fairly ubiquitous, and changes in the low-level jet in the proximity of deep convection is one topic of interest. The stratification, as well as the cold pool that develops through microphysical processes and dynamical processes in deep convection, may trigger an undular bore that may remain linked to the deep convection or may propagate away from the density current, cold pool, and may evolve into a solitary wave train. Here's an example of one of those convective systems or triggering a solitary wave train. And as you look at the surface observations, I'll show that animation again, you can see rather strong winds upon the passage of the leading wave, gusting from the direction pretty much where the disturbance comes from. Yet there's no temperature drop. In fact, in some stations, there's a temperature increase. That's because the stable boundary layer is being disturbed and mixing occurs over a greater depth. But typically, a pressure check does occur because of fairly deep adiabatic cooling as the wave passes. Here's another example over the Gulf of Mexico. This particular wave train of amplitude-ordered dispersive waves actually triggered convection just to the west of this area that's shown. They tend to occur at night, and therefore they're not seen all that much, and they're not seen by visible satellite imagery. But here's one that occurred in the morning in Iowa, and there's a paper on this by Coleman and Nupp. Here we go. In Monthly Weather Review. It's pretty spectacular wave-like phenomena. And strong winds also associated with this at the surface. So this is clearly an undular bore. Some of the bores actually are not undular at all. They are rather discrete transitions from subcritical to supercritical flow with some breaking waves, but not the wave-like appearance that you see here. Essentially, there's three types of wave-like phenomena associated with density currents. One is basically trapped D waves that you can see during the daytime in the convective boundary layer. But here there's a stable boundary layer that may be quite shallow. The density current impinges upon it. The change in the fluid depth, SBL fluid depth, is dynamically not significant. This is a shear-driven amplitude ordering. Typically, KH billows tend to form. There's many observations of KH billows on top of density currents observed during the daytime, typically, in the convective boundary layer. The speed is essentially the density current speed, and the bore speed is less than the density current speed, which is why a bore does not really form. For instance, here we observed this in IHOP. You can see vertical velocity in this panel and radar reflectivity index in the lower panel. You can see a nice temperature gradient and also a humidity change. Continued cooling in red behind the leading edge, indicating essentially a density current. And you can also see some billows behind. And this is dual Doppler observations or single Doppler observations with our radar. And you can see convection developing ahead of the boundary. I can use a stick here. And the wave-like trapped Lie waves behind the density current. An undular bore requires that the bore has a speed exceeding that of a density current. So it can move away from the density current. Waves tend to form. They tend to be dispersive waves, a series of amplitude-ordered waves. It's a fairly transient evolution. It's not much documented in observations. It's mostly, well, there's a number of observations from various parts around the world, but the wave breaking characteristics really have not been documented, and breaking is likely to occur in the presence of a low-level jet and strong shear. Essentially, they're similar to tidal bores that you see here in the Amazon River or Bay of Fundy in Canada. The heights, the various heights that are shown here are important. The depth of the stable boundary layer, the depth of the bore, and then the depth of the density current. And a smooth undular bore tends to occur when the bore depth is 1 to twice as deep as the SBL depth. Some breaking waves may occur when the bore depth is 25 to 50%, or the boundary layer, the SBL depth, I guess, is between 25% to 50% of the bore depth. And when the SBL is more shallow, that's a thin black layer here, then essentially you get a density current like configuration with strong braking, Kelvin-Helmholtz type braking behind the leading head. Finally, you have a solitary wave train, soliton, that is also dispersive, moves away from the density current here, and has a greater depth. Although there's no depth change from ahead to behind the solitary wave train. It's a non-linear phenomena. Bohr shear interaction drives it, and energy is being extracted from the Bohr to drive this soliton. Here's a numerical simulation that goes back many years, Christie 1989, you may have seen this. It's a numerical integration of Benjamin Davis-Ono equations without turbulent dissipation. Essentially, what you see here is a Hofmöller type diagram. Time is shown in the vertical, distance in the horizontal, and the amplitude of the vertical displacement is shown. You can see how in a frame relative to this Bohr, a solitary wave train develops, with the leading wave being the highest amplitude. It's highly nonlinear. Conditions for Bohr formation essentially relate to the depth of the stable boundary layer, which needs to exceed a quarter of the, it needs to be at least a quarter of the Bohr depth. Wave ducting mechanisms that relate to stratification. You need to have a stable layer at low levels and a less stable layer aloft. And also to wind shear. Wave ducting typically requires a critical level to be present, whereby the Bohr speed equals the ambient wind speed. And finally, the Bohr speed needs to exceed the density current speed. And so the conditions are fairly restrictive, which may explain why they're not all that common. The Bohr speed relates to the various depths, the three different depths that I mentioned before, through various equations that are theoretical, based on fluid dynamics. Here's some illustrations. Most of these are over water, and they may be triggered by land or sea breezes over, in this case, northern Australia. They may also be triggered by deep convection. This is a modest example in Central Asia. Anyway, detailed observations of the vertical displacements associated with Bohrs are not that common. We were fortunate in IHOP back in 2002 to have some Bohr observations. They were more by chance than by design. Here you can see various profiling instruments depicting vertical displacements. These are coincident measurements at Homestead in the Oklahoma panhandle. You can see fairly strong and deep vertical motions on the order of 1 to 2 meters per second over a depth that may be sufficient to lift parcels to the level of free convection. And in this case, the sustained increase in depth of the moist layer is an indication of Bohr passage. We had some aircraft observations too of Bohr, and some numerical simulations of this particular Bohr event. The cross sections in distance and time don't quite match, but the simulation shows a fair bit of turbulent kinetic energy in orange here associated with the Bohr. The Bohr is much deeper than the density current, which is here. The solid lines are isotropes. So they can be and have been simulated. The other important phenomenon in the Great Plains to explain nocturnal convection is the low-level jet, which has been documented fairly well, fairly ubiquitous, occurs maybe every other night in the Great Plains in the warm season, especially in central Oklahoma. This is a climatology going back many years, 1968. Essentially, it is in an inertial oscillation that decouples from the convective boundary layer in the late afternoon, evening, and performs a an inertial change in wind direction in the holograph. Strongest at night, mainly between midnight and sunrise, and peaks in height at fairly low elevation. I don't think it's well documented, but in some cases it's just a few hundred meters above the ground. So very strong wind shear at low levels. Another depiction from a textbook. You can see the very strong low-level winds, much stronger than winds anywhere during the nighttime period. I don't think this is a composite. These are specific days in Oklahoma. And thirdly, there is the diurnal variation of convection. It is based on work by I.G. You know the person better because he worked here. My apologies, David. Yeah. Going back many years also. While much of the convection just drops on and off over the southwest, for instance, or over Florida, there is this propagation here. Maybe it's advection, maybe it's propagation from the high Rockies into the Great Plains. It's clearly an anomaly, persistence of fairly high frequencies of high reflectivities into the Great Plains at the latitude that corresponds with the high Rockies. And much of that convection is rather organized. Deep convection tends to be far more organized at night than during the day. The frequency of MCSs, and these are nocturnal MCSs, between 6 p.m. and 6 a.m. local time. Contiguous area at least 40 dBz over a length scale of at least 100 kilometers. And these are two separate years, and there's a lot of interannual variability, of course. But you can see that they tend to occur from western Kansas, Nebraska into the Midwest. And there's a well-defined maximum also in occurrence of lightning in that area at night, and other severe weather phenomena. Another topic of interest in PECAN is the predictability and the use of essentially a mesoscale network of profiling systems to improve predictability or to do experiments related to predictability, data assimilation experiments. This is a composite of 5-week average convection allowing ensemble model runs, showing that compared to observations here on the right, the initiation and propagation of convection, especially into the afternoon and evening of day 2, is captured rather poorly by rather high resolution 4-kilometer simulations. This is part of the hazardous weather test bed back in 2010. So Rich and Carbone say that warm season QPF are the poorest performance area of all forecast systems worldwide. IHOP was largely motivated by that 12 years ago, but that focused on the daytime, and PECAN differs in focusing on the nighttime, when convection may be elevated. This is from Stan Trier's work. He indicates that this convection is elevated, and this is surface-based. How do you know? Not from the radar morphology, of course. You need basically lower tropospheric profiling at a mesoscale in order to be able to determine that. So the key challenge really for regional National Weather Service offices, and we talked to some forecasters just a few weeks ago in a teleconference, whether the elevated convection will affect the surface and produce severe weather phenomena, strong winds, possibly tornadoes at the surface. There's been a number of simulations to address that question, elevated versus surface-based convection. Here's a simulation that at first is elevated, This is a cross-section. This is work by Brian and Weissman. You can see fairly high theta E continuously underneath the convective line. This is a vertical cross-section along the dashed line. And there's an outline of cloud water or cloud ice. Clearly, there's some low-level stable layer and then potential instability in the upstream environment over a depth of some 4 kilometers. This is at time 3 hours, and then 2 hours later you can see that the cold pool has extended down to the surface. Of this low theta E air has made it down to the surface due to maybe some vertical transport, but also evaporative cooling, I would think, producing a more intense bowing squall line. This relates to dynamical and microphysical processes. Matt Parker has this figure that you may have seen, where elevated convection is being maintained by a bore. Some of the parcels at low levels within the stable boundary layer, which is over this depth essentially, remain at low levels, whereas parcels that start at higher levels ahead of the squall line are lifted over great depth. These are tracers released in the SBL, and you can see that none of the tracers make it into the anvil region of the convection. They remain rather shallow. There's a situation where CAPE is elevated. This shaded area is an area where parcels will have positive CAPE when released or when lifted from that level. So there's no surface CAPE. The most unstable CAPE is elevated 1 to 2 kilometers high. And the key point is that there's a well-defined cold pool. This goes only up to 3 kilometers, where these other ones go up to 12 kilometers. So there's a cold pool, and ahead of that cold pool, a small undulation, which is referred to as an undular bore. So it may be that these bores are essential in the maintenance of nocturnal convection that is elevated. There are, of course, large-scale factors driving convection, and in fact, low-level convergence and frontogenesis tend to result in relatively narrow belts along which deep convection tends to travel at night. You can see basically a baroclinic zone and upper-level shortwave contributing to MCS maintenance. Low-level jet typically converges in the vicinity of that baroclinic zone. Tuttle and Davis showed that on average, now this is a composite for 2 months over 5 years, and this is observations, show that precipitation is fairly narrowly concentrated along a corridor. Now this is composited relative to a particular latitude, so it doesn't all happen in that boundary between Kansas and Nebraska. But the point is that it tends to occur in a fairly narrow region wherever that larger scale convergence tends to occur. The weak baroclinicity tends to focus. Another factor, a larger scale factor, is the idea that PV anomalies tend to form due to latent heat release by convection over the mountains, which is strongly diurnally modulated, typically afternoon deep convection. And that then propagates towards the, or moves as a wave, or is advected to the east, and sustains nocturnal MCSs over the Great Plains. It's something is that PECAN does not really focus on, simply because we don't have observations going, at least focused observations over the high Rockies. The PECAN domain is constrained to the high plains. So in essence, PECAN focuses on the link between diurnal changes in the lower troposphere and deep convection. Basic questions are, how is elevated convection initiated? How does surface elevated CI differ from surface-based CI? Surface-based CI is fairly well documented. Radar fine lines are well known to be triggers for deep convection. At night, there are no well-defined fine lines, radar fine lines, or they're not nearly as detectable. According to Wilson and Roberts 2006, based on IHOP, 80% of nocturnal CI events were elevated. Most of them were associated with elevated mesoscale convergence zones that were remote from any fronts or not associated with radar detectable bores or singular boundaries. These radar boundaries just are not there at night. And there's no visible satellite imagery to be guided by either. So elevated CI is something that will be quite a challenge, and it's a target of PECAN. How does the evolution of low-level stratification cape and low-level jet during the night modulate the upscale growth of convection and maintenance of MCSs? And then the basic question about the fundamental, maybe the paradigm of MCS organization may change in the presence of a stable boundary layer and a low-level jet. Those ingredients currently are not included in typical schematics of, conceptual schematics of MCSs. And bores may be an intrinsic part in mature MCSs in the presence of elevated cape and a surface stable layer. Do these bores require a rear inflow jet and a stratiform region? What controls the decoupling of the MCS inflow and cold pool from the surface? How does a MCS become elevated? And what is the diversity of boundary layer disturbances triggered by deep convection bores and solitary waves? So fundamentally, in a nutshell, PECAN is intended to study the deep convection at night over the Great Plains. Dynamics of this convection is poorly understood in terms of the CI, transitions between elevated and surface-based convection, and also the organization and maintenance mechanisms of MCSs. Impact, in general, warm season QPF remains poor. It's actually a little better during the night than during the day because convection tends to be more organized at night. And also we believe that PECAN can serve as a testbed for a nationwide network of lower tropospheric profiling system that was called for 5 years ago in an NRC report, observing weather and climate from the ground up. They actually called for a network with a typical spacing of about 125 kilometers, which is quite dense, corresponds to on the order of 400 profiling systems across the lower 48 states. We're not even close to that at this time. In fact, we're losing profiling systems as we move along and lose the NOAA demonstration network of wind profilers. So key hypotheses that are listed in the science overview document are first of all related to CI, initiation of elevated convection, specifically the internal structure, microphysics, and dynamics of nocturnal MCSs, vertical displacements by undular bores and solitons, and then there's a NWP component, especially related to data assimilation. PECAN will provide a very dense network of soundings, radio sondas, and then also continuous profiling systems. So the experimental challenge is to obtain this mesoscale network of vertical profiles of temperature, humidity, and wind at the horizontal resolution on the order of 125 kilometers. And to my knowledge, the last time a low-level jet was documented at that spatial resolution was back in 1963. By authors were listed simply as NSSL staff. And they came up with these cross-sections from west to east of wind speed of the low-level jet across Oklahoma or northern Texas here, using piebald observations. We don't really know the fine-scale structure of the low-level jet in 2 dimensions. Other than that, we need a good vertical resolution from the surface to about 4 kilometers and temporal resolution to observe these wave-like disturbances that may move through at night and that have been observed by chance in the past. The pre-convective environment and the MCS life cycle needs to be documented, both within the MCS and in the clear air. Different instruments are able to do different things. For instance, within the MCS, LiDARs will not work. Raman LiDARs, for instance, but passive microwave radiometers may. Those radiometers have a relatively poor resolution, so there are advantages and drawbacks to the various systems. So the experimental design that we have consists of a series of radars, scanning ground radars, SPOL, and the AT-AT network, of course, and then 4 radars at the ARM SPG site, SGP, Southern Great Plains site, are part of the network. We have 6 X-band radars. They are, let's see, the 3 DAOs, the 2 SMART-Rs, MIPS, UAH has an X-band radar called MAX, I believe, and then there is NOXP, and there may be one more, RAXPOL. Let's see, aircraft, the King Air with WCL up and a compact Raman LiDAR down. NASA DC-8 will have LACE, which gives you water vapor profiles, and interferometer, which gives you temperature and humidity profiles. And then the NOAA P3 will be flying its X-band fore and aft scanning tail radar, as it did in lots of hurricane experiments and in Baymax, for instance. And then there will be some mobile mesonet vehicles and sounding vehicles. We have a compact Raman LiDAR, which we used in the Laramie area that depicts basically humidity. It's a Raman humidity. In this case, a dry line. Laramie is out here, Cheyenne is out there somewhere, and we can see a very well-defined dry line humidity gradient from the surface up to about 500 meters higher. This Raman LiDAR is not as powerful as the more advanced temperature humidity LiDAR that we had hoped to deploy in PECAN, but at night it should have a better coverage than what you see here. Then we have a new concept, really, the PECAN integrated sounding array. The idea is to have kinematic, thermodynamic, and moisture information. Of the lower troposphere, we'll have 10 units, 6 of them fixed and 4 of them mobile, all containing surface meteorology, radio sonde, a wind profiler of some type, and then moisture and or temperature profiler. Key challenge for the mobile units is to deploy these facilities ahead of the target at night. Deployment ahead of any severe weather during the daytime is challenging. Doing it at night will be even more challenging. We're working on a network of potential sites that are well characterized, on the order of 500 sites across the central Great Plains. We'll have a good forecast team led by Bill Gallis, and then we'll work on coordinating the deployment of the mobile radars and mobile PISA units. And I think the intent is to have them deploy just before sunset, which will require good forecast guidance, of course. Here is a set of the fixed PISAs, FP1 through FP6, and this is something Dave Turner is coordinating. I highlight the EOL units. Bill Brown's name is mentioned in several of these units. I have to travel around a fair bit to coordinate all that. It's unique, I believe, to have such a mesoscale network of profiling systems using state-of-the-art instruments, LiDARs, Raman LiDAR, mini dials are mentioned here under development. And then ARIES also, and passive microwave radiometers. We have a number of ARIES from DOE There's one here, one here, one here. They give you temperature and humidity profiles. Doppler lidars also. And then on the mobile side, we have 4 units. So these, whereas the fixed PECAS will work 24/7, at least that's the plan, the mobile unit will operate during IOPs only and will be positioned strategically. The network will be deployed, the mobile network will be deployed within the PECAN domain, more or less, shown as a dashed box. SPOL is located here. The NOAA P3 and NASA DC-8 will be deployed from Salina, and the King Air from Great Bend. Hayes, the operation center, is right here. The contours that you see here, this is the low-level jet frequency, basically every other day in July. These contours are an indication of the Nocturnal MCS initiations per month. They tend to be most common a little bit further north towards Nebraska. That is work by Conrad Ziegler's group. And so the fixed PECAS are located at sites within about 75 kilometers of the either SPOL or the NEXRAD radars for good low-level coverage. 75 kilometers is about the maximum distance to see these solitary waves or bores propagate at night. Low-level coverage. I think I mentioned all that. So here are the ground-based units again. The fixed PECA units. The Hayes is right here. And the King Air will be flying a track that is mentioned right here on 5 missions, some 20 flight hours in the vicinity of SPOL to document the low-level jet under quiescent conditions. Here's one of the mobile units, clamps under development, David Turner and Petra Klein from OU. Key instruments are the Doppler lidar, passive microwave wind profiler, and ARI. Both of them basically profile temperature and humidity. And all these units also have radio sonde release capability. Mobile PECA-2 is MIPS, which has been around for some time and is continuously being developed by Kevin Upp at UAH. Number 3 is Spark by Wayne Phelps at the University of Wisconsin. Also has an ARI and a Doppler lidar. And then we have MIS Mobile, ISS, with 915 megahertz wind profiler and radio sondes. And the T-Wolf FMCW radar will actually be operating with FP or MP3, Howie Bluestein. We have dedicated 5 IOPs to CI, 5 to board, and then 10 to MCS, dynamics and microphysics. And on a non-interference basis, we'll study the low-level jet with limited resources. Here's a MCS mission, idealized, highly idealized, linear convection, trailing stratiform region. The mobile platforms are to be deployed ahead of the approaching MCS squall line. A hexagonal structure with 7 mobile radars making up that structure, with 1 in the center and 6 on each corner of the hexagon. The mobile PECAS will be in a linear array across the approaching MCS, or they can also be aligned in another pattern along to look at long band variability of the outflow boundary bore and the MCS. All these units are to be stationary during the passage of the MCS and basically sample the pre-storm environment, the storm, and then the post-storm residual cold pool. The aircraft will be traveling basically with the boundary. The King Air will be in the proximity of the MCS. Pilots want to stay away on the order of 10 nautical miles from the convection. Actually shown a lot closer than that. And NASA DC-8 will also sample the pre-storm environment at a higher level. NASA DC-8 will be flying at 10 kilometers, whereas the King Air will be flying step traverses and these lawnmower patterns at low elevation. And then the NOAA P3 will be flying similar to BAMX in the trailing stratiform region, approaching the squall line from behind, doing a spiral descent, a spiral ascent, mainly for microphysical purposes, another spiral descent, and then a stepped series of cross sections through the trailing stratiform region to document the vertical structure of the precipitation. That's mainly the work of OU, Konrad Ziegler's group, and then University of Illinois, Greg McFarquhar and Bob Rauber. Bohr mission. Sorry, no, this should be CI mission. There's a typo there. This is convection initiation, and you can see a line of. No, it is Bohr. I get confused. Okay, so there is some convection up to the north, and Bohr emerges from it, as you saw in the animation earlier on. And the idea is to sample any disturbances in the nocturnal boundary layer and their interaction with the low-level jet, which is shown as a bold arrow here. The source of the Bohr could be a cold front, although they become quite rare in June and July. And then this is a CI mission. Okay. So CI here occurs in the baroclinic vicinity, just north of a stationary boundary, maybe. And we would be flying across the area of mesoscale convergence, as shown by the low-level jet core decelerating in this area. And as long as convection is not too close, we'd be flying across. Otherwise, afterwards, we'd be flying a pattern like this. That's the King Air. NASA DC-8 would be flying at higher levels over a longer area, covering the moisture variations over a greater area. Racetrack patterns or else 9270 return tracks over the same flight leg. And then we'll also fly low-level jet, as I mentioned, under non-interference basis, doing both sawtooth patterns and fixed elevation legs, very low elevation along a track that has been preset to be away from houses and also any towers. Similar to IHOP, we had a set track. So in summary, PECAN is the first campaign to focus on continental, nocturnal, deep convection, organized convection. We'll explore the dynamics of MCSs interacting with the stable boundary layer and the low-level jet. And it should serve as a rich data source for data assimilation experiments and also a demonstration network of lower tropospheric profiling systems. That's all I have.
Got plenty of time for questions. And also, I'm told that our beverages may actually be outside. So if people want to slip out and back in, that's okay too.
So why does the low-level jet slow down at that particular latitude that you showed?
Stan, you want to give that a try?
Well, there's usually a lot of times.
There could be a lot of reasons for that. Primary reason is these convective environments in which you have the low-level jet, there tends to be a large-scale deformation pattern in the synoptic scale. And the flow is northerly to the north of the front. So the jet doesn't penetrate to those latitudes. So you just have a kind of a streamline pattern would look like that.
So that requires a pre-existing synoptic?
Yeah, typically, yeah.
But I would add that many MCSs will be devoid of any measurable baroclinicity. There will be situations in July in particular where we really don't see any more than 1 or 2 degrees maybe over a scale of hundreds of kilometers kind of temperature variation. No well-defined surface boundary. Synoptic forcing can be rather weak, as you know, in the summer. So, and that also adds to predictability question.
What will be the signatures you will be looking in any of the forecast models? And I assume you will have a massive forecasting effort in order to plan these missions. What specifically, what ingredients will you be looking for in these forecasts? National, I'm talking about weather prediction and mesoscale models for that matter, for these internal bores. Those are fine scale phenomena that are fairly hard to get. To simulate, you need high resolution in order to get things right.
Yeah.
Not just the high resolution, other ingredients as well, but high resolution is one of the keys.
Yeah, well, the surface network is quite dense. That all that surface information becomes largely irrelevant when the phenomenon of interest is elevated, elevated deep convection, elevated CI, low-level jet, and especially these boundary layer disturbances. They're difficult to forecast. And Steve Koch is working with Stephen Hagi at OU to develop and test a set of forecast criteria that then will be used by Bill Gallus's forecast team to predict the occurrence of bores. We had a dry run last June where the forecasters were tasked to give us an outlook of the probability and timing of bore occurrence, and it is quite difficult. It relates to the presence of a cold pool, first of all, either frontal cold pool or more likely an MCS cold pool. The depth of the stable boundary layer, which is really not predicted well, and then the low-level jet itself is important. I think the PECAN field campaign will be a learning experience. It's really not been predicted before, bores, and as I said in IHOP, we encountered them by chance.
I was wondering how important the daytime is in generating the conditions for the night. So if all your resources are mobile in the early afternoon, does that preclude seeing a development of what goes on at night?
Yeah, this has been a topic of discussion in the PECAN group. Boundaries that form during the daytime in the convective boundary layer, they tend to be on a smaller scale baroclinic, solenoidal, and they may persist as a stable boundary layer forms below. So they may persist within the residual boundary layer, and they may act as loci of convergence, and they may trigger convection that may grow upscale. And I know Kevin Knupp is in particular interested in this afternoon to evening transition. Bluestein talks about this sweet period when the surface boundary layer develops for deep convection to form. Can PECAN address that? Not really, maybe to a limited extent, but we really want to focus our resources to the period after sunset, which is relatively unexplored. But certainly the afternoon development, cold pool development, or whatever boundaries may develop due to daytime convection will have an impact on nighttime convergence. It's something that we, again, will have to explore during the field campaign. There will be larger scale sources of convergence for CI, and then there will be maybe locally induced convective sources of convergence.
What are the dates for the field campaign?
It's 1st of June through the 15th of July next year.
Given all these challenges with predicting what's going to happen, how much flexibility do you have to switch from one type of mission to another? How quickly can you reallocate your assets? Because something may evolve in something different than you expected, and by being flexible, you may still capture that other thing that's evolving.
Yeah, that was one of the objectives of the dry run I mentioned earlier. Work with real weather to see whether our preconceived mission, virtual mission, was a good choice, and how we could redeploy if necessary. MCS and Bohr missions tend to be fairly complementary. If a wave-like phenomenon moves away from an MCS, which we cannot really predict, we can position certainly the aircraft and maybe the surface mobile facilities to capture that for Bohr missions. CI, I think, will be especially difficult at night. Really, because we don't have that guidance that exists during the daytime. I remember in IHOP we worked with well-defined radar fine lines that forecasters were monitoring. But zoomed in on that, flew back and forth, and had all the surface assets in the vicinity of that developing boundary. But if you don't have this boundary, if you only have numerical guidance to go by, I don't think CI will be easy. It's also a specific point in time, whereas MCS has a long lifetime, as CI as an event, at least. I may be wrong, Tammy, but ideally you capture that moment in time where deep convection first develops. So I think that will be a real challenge. So good forecasting guidance is essential, and we are very fortunate to have Bill Gallas and several forecasters from NSSL, retired forecasters, to work with us.
Well, if there are no other questions, let's thank Bart again.